Okay, let me share my screen here. And then I have this. Okay. So in the beginning of the class, let me first mention one thing, which is the homework assignment. I've sent email to everyone about the homework, and I know some of you may want to audit it. I'm actually not sure because this is a kind of like a certificate course. So I've already sent an email to Bill to ask whether he can help, because like for formal classes, I know it's kind of like you can make it to be audit, and then in your final transcript it will show audit. But for this course, I'm not sure. Of course, if the definition of the audit is purely just say, hey, I just want to listen, what I mean, instead of I really want a certificate, then of course you can do whatever you want. So the homework is right here. Homework. You got homework. So where the problem? Here the problem. I believe only two problems, three problems. The first problem is a very fundamental problem, and the second one, oops, uh, it's a bit slow. The second one's a bit requires a little. Maybe I should download it too slow. Just Okay, here we go. So the first problem is very fundamental. The second problem is something. Let me see. The second problem is something. Tells you a trick. Basically, how can you actually run run a linear model for actually a linear regression for a nonlinear fitting? So here we use a sin x, and you can. I forgot the details, but if you did it correctly, you will see something like that. So I believe it will be something like that if you did it correctly. And then have fun. And you will see actually that's very interesting that as long as by those kind of as long as I recode some parameters, I can make something like this way. And the third problem is oh okay, nothing, just the ridge lasso comparison and a feature selection. Basically it will be the example that we will show today, and also I believe the last example we finished. And the homework is due Monday, which is this day, next Monday, not yesterday, no worry, so that you do have a weekend. As long as you spend some time, it won't be too difficult. I believe only problem number two may be a little tricky, but if you're familiar with the concept, that should be really direct. Okay, and we should have 2 to 3, probably 2, because I count the weeks will finish here, so we probably don't have so much time. So probably 2, and I'm gonna remove the midterm exam, so it's gonna be like this. Where this homework 70%, and the final exam gonna be 30%, and final exam gonna still be like take-home exam, so no worry. So of course, like open book means we don't have the book, means that we open the slides, you can do whatever you want. And that's also the reason that I do not want to provide you directly the code, because I know if I provide you directly the code, many people may just copy and paste, which is I don't want. Trust me, no matter how skillful your coding is, write everything by yourself. Instead of just looking at me doing it, it will greatly help you understand the concept or the mathematics, because I know many of you are very, very good in Python. Maybe your Python skills are way better than mine. But I believe the reason you want to, have a look at the core or study this course is to get familiar with the concept, and the coding, the thing will significantly help you. Okay, so this is about homework number 1. And again, here's one more thing. All the I believe I have a playlist here. So all sorry, you can ignore some other things, which is some personal connection and also some previous courses, but videos. So all the videos are uploaded here. So in case you're busy, you cannot take a class, something, you can just watch it here. Okay, now let's continue our class. We lecture number 6. Okay, here we go. So I believe in the last class we let me go through it very fast, because the concept here is really, really important. So we mentioned the concept of overfitting, underfitting, and good fitting. And then we mentioned the challenges, which is what if n is less than p plus 1, or n less than p, Or another possibility is with extremely small or large absolute value, in one or in some elements of beta, which will dominate or will vanish. How can we handle these issues? And that's why we need to improve the LSR, least square linear regression, which is to add regularizations. So how to add regularizations? So basically we have three ways of the regularization: beta 0 norm, beta 2 norm, and beta 1 norm. So they are corresponding to best subset selection, which is for beta 0 norm, where it is here. And then for beta 2 norm, which is the Lasso regression. So Lasso regression. By the way, some of you may ask, why do we need to focus on the beta norm? Simply because beta plus beta 0 itself, okay? Beta is the only variable that we want to figure out. Again, for linear regression, we do know X and Y. They are all observed or all training data. We know it. What we do not know is the beta. So of course, then how to add the regularization, we cannot add a constant in an optimization problem. You add a constant is nothing. I mean, yeah, it's just a waste of time. The solution will be exactly the same with or without a constant. But the variable regularization, that's the same. And here, we have the beta 0 norm, beta 2 norm, sorry. Beta 0 norm, it's a nice concept, but it's not that practical because, again, this is it can be showed that it's an NP hard problem, which is, well, really not easy to be solved. Like in practice, even if P is 200, it's already gonna take you some time. While in the real case, you could have millions, even billions of P's. So, it's not practical. Then we have the ridge regression, which is to add a two norm. The two norm is nothing, just our Euclidean norm, and we know that for, let's say, x squared plus y squared less than or equal to 1, this is a circle. I mean, this is middle school mathematics. And then give me 1 second. So this is the form of the regression. Let me add a box here. Okay, so I have a box here. So, and the so-called regularization means what? Means this part. And you can see the first part is nothing. Let me just remove this again. Let me draw a box here. Let me use let's say this color. So the first part here, this is nothing but just the least square linear regression. The tricky part is the second part, which is L2 regularization part. And so this is beta 2 norm, because by definition, 2 norm means what? Sigma of AI square. So here with beta, so sigma of beta J square. So this is the thing. Okay. And then it will have a kind of like element shrinkage. Why? Because of this. So we can see that. So the original beta is here. The beta ridge regression, the solution would be here. And you can see no matter, in the direction, let me plot here. No matter in this direction or in this direction, it is smaller. Let me change another color. By comparison, you see my beta OLS, the original beta 1 is this length. And my beta 1, original beta 2 is this length. Now by comparison, see, my beta 1 ridge is this length. By comparison, this one is longer. And similarly, for the beta 2, it's also longer. So it's a shrinkage. So why do we need to have a shrinkage? Because given a shrinkage, everything gonna be smaller, so that I can kind of like regularize the case. Let's say if something is very, very big, or if something is really, really, very small, after shrinkage, it will be even smaller. Then you may want to have a threshold. Let's say if, for example, if beta I is less than or equal to, let's say 0.001, then I'm gonna ignore it and then make it vanish. So, you can make something like that. So that's the thing. I realized that in the last lecture, I forgot one thing, that is, people may ask, so why do you, let's say, write the contour lines to be ellipse? Why don't you kind of like write plot them kind of like a circle or whatever the shape, a box, that's because here, I better click this one. So so this is a matrix representation of conic sections. So basically, we will have a look at, because here, here's just, this is a very regular case, which is 2D on X and Y. And here we also plot as 2D, but for higher dimensional, the same thing. So basically, we're interested in this matrix. And then depending on how this matrix look like, the determinant of this matrix, the conclusion is going to be different. So it will be the contour, it will be an ellipse if and only if the determinant is bigger than zero, strictly bigger than zero. Okay, and you can clearly see this is of course strictly bigger than zero. Why? Because here I assume give me 1 second. Here, because I already plot the OLS solution. If I plot OLS solution, that of course means OL solution exists. Otherwise, I cannot plot, right? OLS solution, ordinary least square solution exists. That means what? That means this one must exist. Remember? Because of this. Where this? Let me see where. Okay. Remember the OLS solution is this one. See it? So I say OLS solution exists. That means what? That means this XTX is invertible. Otherwise, it's invalid. How can you exist, right? So this is invertible means what? Means that where is L2? Okay. This is invertible means the determinant is strictly bigger than zero. And the same thing like here. So, and that's the reason why I plot everything to be eclipse instead of, other like those kind of conic, conic lines or something. So that is the reason. Okay, and the third thing is the Lasso regression, which is L1 norm. L1 norm, be careful, is the summation of the absolute value. So again, by just middle school mathematics, you will see that if the L1 norm of a vector A is less than or equal to 1, it will be just a diamond, and all this will be 1. Of course, it doesn't have to be 1. I mean, 1 is just to show you can be less than or equal to t. So all here will be t as well. Okay, now the Lasso regression, because it's a diamond, so what's going to happen is that you have a high chance to get the solution to be somewhere at a corner. Being at a corner means what? Means some parameters will vanish. For example, in this specific case, which is beta 1 plus beta 2 is less than or equal to t. So this will be t, this will be t, negative t, negative t. And hence, here you can see in the Lasso regression, my beta 1 is what? Sorry, not beta 1, my beta 2, sorry. My beta 2 is 0. In other words, here in my Lasso regression, it's 1D. You know what I mean? It's not 2D. However, in beta OLS, it's still 2D. And again, we can plot something as we did before, which is, so this is the original beta OLS, the length of beta 1. The length of beta 2, sorry, where it is. What did I do here? Okay, come out. Okay, here we go. Beta 2, and then I can plot, let me use another, let's say yellow color. I can plot beta 1s here. And indeed, you can see it's a shrinkage, isn't it? This yellow one compared with this green one in the direction of beta 1, it's clearly smaller. In the direction of beta 2, it even vanishes, it's 0. So that indeed, first, it's a shrinkage, and second, the most important thing is it is a feature selection, meaning that by Lasso, I will directly select feature 1, which is beta 1. I will ignore beta 2. In other words, this problem will be 1D. So again, people may ask, so what's the point? 2D to 1D, so what? So what it means that in your future test or in your future application, you no longer need to consider feature number 2. You only need to consider feature number 1. It will greatly save your resources, your cost, your everything. And here's just 2D. What if you have, let's say, 1 million dimensions? And the thing is that in the 1 million dimensions, it depends on your data, the result, but it's possible that you can make it something from 1 million to 300. I believe I have an example, which is the last example. I believe that there's shrinkage about 94%. Shrinkage 94%. In other words, if you have like 100 parameters, it will shrink to only 6 parameters. Think about it, how powerful it is. It's super, super powerful. Okay, here's a comparison. And now, after we mentioned the cross-validation, steps are here, or if you're not clear, just have a look at these 2 examples. I believe they're pretty simple. And I believe, no, I don't have to take it, but if you're interested, you can just code it by yourself. This is actually super simple coding, just 2 force down. If you are not familiar with Python, especially, coding this one for fun will be very helpful. Anyway, and then we, let me see, did I finish this example last class? Let me see. Oh, yes. I believe I've finished this example. So in this example, it's a small data, very, very baby data, which is just here. again. Which is just I have 6-dimensional data, and then I have 100 maybe, yeah, 100 observations. So it is 100 by 6-dimensional, but 100 observations. And here to make sure that my result will be the same as this one. So I fixed the training data, in which the first 70 data among the 100, totally 100 data to be the training data, the last 30 data to be the test data. And then this part is how to run the LSLR. This is how to code the ridge. This is how to code the lasso. And then we have the comparisons of these things. And first of all, indeed, there's a shrinkage. Second, you can see in lasso regression, there's a parameter selection, which is it's gonna kick out parameter number 3. In other words, now I only need feature 1, feature 2, feature 4, 5, 6. I don't need feature 3 anymore. And the second thing is by the cross validation, the lambdas, give me 1 second. I believe what are my lambda selections? Okay, so I give the lambdas list to be 1, 3, 5, 10, 20, the same thing for lasso. And finally for ridge, both of them actually selected lambda to be 1. By the way, this is just a coincidence. It's not, Lasso and ridge in general, they will not choose the same lambda. I mean, this just coincidence that they happen to choose the same lambda in this specific example. So this is lecture number 5 to the number 6. Is it number 6? Yes, number 6 to example 6.3. And now let's run the next example. The next example will be a bigger data in which my n is still 1,000, but my p is what? My p is 10,000. And then here, basically I will have 10 million, this one times this one, observations. It's technically it should not be really called the observation. I should say 10 million, kind of like the single, scalar data. So looks like a big, well, actually still very small. We can even make much bigger data, but it will take a long time to calculate. So I don't want to waste the time in my class. If you want to, you can go to Kaggle to download the tons of data, like the data could be gigabytes, so it will, but basic ideas are the same. So let's see, how can we do this one in which it is bigger data. Okay, so first of all, let me I believe I opened Anaconda already. Let me open the Jupyter notebook. Okay, so where it is here, lecture 6. Yes. Okay, so so this will be, let me see, example 6.4. By the way, here one thing I want to show you is that we can make it a markdown, so I can make it like this way. This means the head. Example 6.4. Then I just need to run it, and it's gonna show like this. By default it's the code, but you can make it to be a markdown, so if you can provide you some format. Why we can do this? Because this is Jupyter notebook. By being a notebook, you should be able to show those kind of things. Okay, so first of all, I'm just lazy. Let me comment and paste all those kind of things. You know what? Actually, I can copy and paste everything stuff only this. Okay. Okay, so what's the name of the data? Ridge lasso. Okay, so it's going to be ridge lasso. Okay, and then let's see, we will need to change something. So I believe I've also okay, similar things here. In order to get to the same result, I fix the data to be the first 700 data to be the training data, and then the last 300 data to be the test data. But again, here's the only reason I do it is just, is just to guarantee that we will have the same result. In practical, you still need to have the, psychometric data split, and then the test data and the training data. Remember what we did in lectures 4 and 5. Okay, so here's just, just an example. I want to fix the results. That's why I do this. I agree, it's kind of like cheating. Okay, so -300. Here's positive 700 and negative 300 as well. So here we have what? We have the initialization here. We get this one. And here we have the MSE here and blah, 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 the MSM training data, test data here. Okay, because I remember we counted the non-zeros here. Yes. Okay, yes, yes. Let me count the non-zeros. So let me show you a comparison here. So I totally should have 10,000 data, right? Oh, so 1,000 data, no, no, not 10,000 data. I total have 1,000 data and I total have 10,000 features, sorry, in which the first 400 features are binary features. I'd better open the data first. It will take a little time for Excel to open it. It's not too small. How large it is? About 56 KB. So okay, here we go. So let's have a look at it. Let me make it smaller. It's just, oh, okay, okay. So you can see that, in the first, in the okay, in the first from X1 to X400, you can see all the data are 0 and 1s, so they're binary. Where's the 400? 400, come on, come on, come on, come on. Oops. 400 is here. So all the data are 0, 1 binary. But after 400, from the 401s, from the 401s to the end of the data, all of them are just those kind of, continuous data. So let's see what's gonna happen. So here I wanna have one thing, which is to print. Let me see. What should I say? Among, let's say, 400 binary features, among the first 400 binary features, this number of them are non-zero by LSLR. Okay, so what does this mean? This is np dot count non-zero. If I remember correctly, I may need to search for it. Let me see. np dot count non-zero, correct. So and then I'm gonna do LR dot coefficient. Okay, these numbers are non-zero. And then I will do the same thing. Oh. Among the 9,600 non-binary features, are non-zero bias. Sorry, here I realize I have a mistake here. It is not gonna be this way. It will be 0 to 400 because we totally have 400. And here it's gonna be 400 to all. So people may question, well, your first non-binary, starts from 400, right? 401, not 400. The reason I wrote 400, don't forget again, in all indices starts from 0. In other words, the 401 index, the 401 variable. Let me close this one. The 401 feature, the index is 400 instead of 401. So what I mean is this one. Okay, this one. So it's the 401 feature, right? But the index in Python is 400. Why? Because the first feature, the index is 0. So okay, so this one by SR, and then I can copy and paste to do all the things here. For ridge, the same thing. But here I need to make it to be ridge R by ridge. And then same thing, do it for lasso. Oh, wait, did I make the name correct? Yes, ridge R and also lasso R of them by lasso. Okay, let's run it. It will take a little time. Okay, great. It will take a little time, and you can clearly see the calculation time of lasso is way longer than a bridge. See it? Many people may question, so why do we need to use the ridge since we already have lasso, which is more powerful? True, but the thing is, ridge the calculation is way faster than lasso. That's the thing. Okay, so here we go. So, there's no surprise that for LSLR and ridge, for both of them, there's no feature selection. No feature selection means, like for LSLR, we have 400 binary features. All of them are non-zero. Similar, 9,600 non-binary features. All of them are non-zero. And for ridge, the same thing. And indeed, uh, 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 there's no feature selection here. However, look at the lasso. Some very, very interesting thing occurs. Among the 400 binary features, 6 of them are non-zero. You know what does that mean? 6 of them are non-zero. In other words, 6 over 400 equal to what? 1.5%. In other words, 98.5% of the binary features are eliminated. How strong it is? Only 1.5% are kept. And here, among the 9,600 non-binary features, 521 of them are non-zero. In other words, Lasso chooses 521 over among 9,600. So I can see 501 divided by 9600, 5%, 5.4%. And this one is 1.5%. How strong it is? And then the total number is, so 6 plus 501. The total where it is 6 plus 501. Even if we consider total, it's only 527. But originally we have how many? We have 10,000 features. So it is actually, in other words, there's a almost 95% of feature reduction. It selected only about 5% of the features, and almost 95% of features are reduced, are ignored, you can say. So this is the power of lasso. But indeed, the shortage of the lasso is the short of the lasso is that, sometimes the calculation is not that fast. It takes some time. By the way, some of you may ask a question that, hey, you mentioned that when P is greater than N, technically we should not be able to solve, which is on the second page. Fourth page, sorry. We should not be able to solve LSLR, right? Because this is not invertible. The inverse doesn't exist. But why here in here, scikit-learn can solve the solution? It doesn't make sense. Okay, the truth is that here it doesn't, so the code here, if I detect something is not, let's say it's not invertible, what it will do is it will try to calculate the pseudo-inverse matrix. And that's how it was calculated. In other words, this solution is not a analytical solution. It is just by pseudo, use a pseudo invertible matrix to replace the invertible here. So the inverse matrix here. So that's how it was calculated. Well, still better than nothing. However, in this case, I would say the result of lasso really dominates the other two. The reason is super clear. Just okay. That's about everything I believe for the lasso sorry, for the linear regression. Any questions here? And the homework one, by the way, is for linear regression. No. Okay. Now let's go to lecture 7, which is okay. Finally, we start classification. Okay, so lecture 7 is about KNN, K-nearest neighborhood classification. So first of all, let's review what is classification again. Classification is one of the most important element in supervised learning and pattern recognition. So for classification, basically each observed data will include a response variable. We call this response variable the label, telling which class or category the number of the class will tell you which class or category this data is, and the number of classes is known. And then for the target is for a new data or for target data based on the training data, we want to predict its class. So for example, let's say we're given 1,000 pictures of cats and 8,000 pictures of dogs. So each of them, for example, is a picture of 200 by 200 pixels with a label cat or dog. So for example, let me let me just cat or dog. So for example, I can give you pictures. Wait here. No. Let's say suppose the left picture, and then here's an input picture, and then with a label 1 from label 0. 0 means cat. The right picture, also this picture, give you a label 1. 1 means dog. And then suppose I give you now suppose here we go. Now suppose I give you so many pictures. Then I will give you a new picture, which is for example this picture. Question: is it a cat or a dog? So this is the meaning. And here the label is cat or dog. And then didn't you see that this is actually very similar with linear regression? Because we can write it like this way: y equal to fx. This x means the picture. We can always vectorize, this. Let's say 200 by 200 pixels. Later we will see a ravel command in Python. The meaning is that to make the matrix to be the column by the rows to be a vector, so that I can rewrite this 200 by 200 pixel image to be a 400 by 40,000 by 1 vector. And then this vector is the x. But what is y? Y is just an integer, 0 or 1. For example, 0 means cat, 1 means dog, like this. The only difference is that in most regression, when I say regression, means the linear regression programs that we've seen from lectures 4 to 7, is that this y is a continuous number. It can be 1 to 1.1, 1.2, 3.4, like those kind of numbers. But here in classification, the y belongs to an integer set, which is 0 or 1. For example, sometimes, so let's say -1 or +1, So this is the same, but their basic ideas are the same. This, still we can run everything to be y equals to fx. Okay, so now, excuse me. Now, we observed the observed data. Each observed data can be written as in this pair, which is x and y. Be careful, x is a vector here, okay? It can be very large, like what we said, 40,000. Y is just a scalar, which indicates an integer class of the category. Okay, then if f is a linear function, then it's called a linear classifier. And for I believe more than 50%, 60, almost most, I would say, classifiers you learn in this lecture are going to be a linear classifier. And for how can we make it nonlinear, simple kernel technique? But anyway, later we will mention about it. And then the domain of y is usually an integer set. So suppose we totally have m classes. The most popular class that we have is c equal to 1 to m. Or sometimes we make it to be 0 to m-1, like Python index uses 0 to m-1 instead of 1 to m. And then specifically, if m equals to 2, which is a binary class problem, we usually use c equal to -1 and a +1. So why don't we use 0 or a 0, 1 instead of -1, +1? Later, especially in SVM, support vector machine, you will see a big profit in modeling if we use -1 and a +1 instead of 0 and 1. So, okay, so this is the basic concept of classification. There are actually many classification methods. Here in this class, we'll just mention several very traditional ones. For example, today we'll mention KNN, and then next lecture we'll mention naive Bayes, logistic regression, linear and quadratic dominant discrimination analysis, and then support vector machine. And be careful here is just the pure machine learning classification methods. Later, if we have time to mention, let's say neural networks, that's completely another level. But here, just a very fundamental group of methods here. Okay, so first of all, what is KNN? So let me make it bigger. What is KNN? So first of all, the name of KNN is the K nearest neighbor, K nearest neighbors. And then let's consider these two cases. So suppose we have these kind of blue circles and red diamonds. All of these are observed data. And then these triangle 1 and triangle 2, these two are the target data. So okay, now suppose I don't have this data. Let me just try to give me a second. Let me try to cover this. Sorry about that. Let me use the red color. Give me a box. Okay, now I just use Zoom, the tool to cover it. Okay. Okay, now suppose this is your observed data, okay? Okay, Now I'm gonna say, hey, show me the group of these two target data. Which group, which class does does data one belong to? Which class does data two belong to? I believe everybody gonna say, oh, simple. This data one belongs to class one, data two belongs to class two. Why? Simply because they're close, right? I mean, this data one is among the groups of class one, and this data two is so close to, the group of class observed data or training data of class two. That's why. Indeed, this is exactly the meaning of KNN. Very simple, right? Okay, now let's formally define it. For a given hyperparameter K and the target data X, X is unknown label, okay, because Y it's a target data, it's not a training data, okay? We classify X by the majority class label of its K nearest neighbors from the training data. What does it mean? Okay, again, suppose, let me still play the same thing. Okay, zoom, let me do this, zoom. Okay, let me cover it. Okay, now suppose we have three groups of training data. After the training data, red data is diamond, heart data, the orange heart data is class, diamond is class 2. This orange heart data is class 3. The blue circle data are class 1. These are all my training data. Of course, here I make it to be 2D. I mean, to visualize it to make it easy for understanding. Okay, now I will give you parameter K. So here, to make it understandable, I consider three groups, three Ks, K1 equal to 1, K2 equal to 6, and K3 equal to 10. Now, I'm gonna show you my target data or my test data here. My target data, I should say. I'm gonna ask you, hey, tell me which group it should belong to. So now we consider K equal to 1. K equal to 1 means what? One nearest neighbor means that nearest neighbor, right? Okay, which data is that nearest neighbor of this target data? So here circles are all, centered at the center of my target data. So clearly this one is my closest data, right? My nearest data, training data, which is the closest to my target data. And what is the class of it? It is class 1. So if K equal to 1, I would classify this target data to be class 1. In other words, 1 and n for the target data, the prediction is class 1. Okay, now let's say K equal to 6. Okay, again, I just plotted this. That means I only consider the 6 nearest data. Okay, 1, 2, 3, 4, 5, 6. So in this circle, this purple circle are the 6 nearest training data to my test data. And then see, I have 1 class 3, 2 class 1, and a 3 class 3, three class 2s. And then again, we classify X by the majority class label of its K nearest neighbors. Here, K equal to 6. In other words, we should choose what? We should choose class 2 because it is the majority. We have 3. Okay, now what if I choose K equals to 10? Again, in this circle, is all the 10 nearest neighbor of my target data 1 2 3 4 5 6 7 8 9 sorry 1 2 3 4 5 6 7 8 9 10. Okay, 10. I just want to make sure that I passed the elementary school. Okay, so here are the 10 data, and then which one is the majority? We can see I have a 5 heart here, 3 diamond here, and the 2 circles here. So clearly the majority is what? Is class 3, the orange heart. And hence, I'm going to classify it to class 3. You see what I mean? So this is the idea of K nearest neighbor. And of course, by different case, your conclusions could be very different. So one thing is how to choose K. Again, you can use cross-validation. But here, in this class, the point is not cross-validation. So I assume, okay, K's are given. Okay, now this is a fundamental, the very first example, how to do it. However, I need to cheat the reasons because I cannot remember the parameters. Give me 1 second. Let me, okay, Canada can be closed. This can be closed. Let me create a new one. Lecture 7. KNN. Okay, so here we are gonna code the KNN, and the very first thing I'm gonna do is, of course, still import everything, right? Okay, I'm gonna import numpy as MP, import matplot lib.pyplot plt, and then from scikit-learn sklearn dot neighbor, I believe neighbors, import k nearest neighbor something, k nearest classifier. Okay. And now I'm gonna first generate some data. Let me write generate the training. Here, since it's a fundamental example, so I just simply generated training data. Here I need to open my cheating sheet because I remember when I generated data, these parameters doesn't matter because it will affect the next example. X1 equal to mp.random multivariate normal of 10, 10, 6, 36, 50. Then y1 equal to np dot ones 50. Okay, so np dot ones 50 means 50, all of them are ones. For example, we can print y1. And what you're gonna see is all 1, 1, 1. Uh-oh, great. What's wrong with that? That must be the parameter. Oh, okay, here we go. That's what I hated. PyCharm will directly close this for you, but unfortunately, Jupyter Notebook will not. Why this one is wrong? Oh, because this. Okay, it closes here. Great. Okay, so here we go. All 1, 1, 1, totally 50. So this is let's say, or you can say 1, 1 dot shape, so that you're gonna easily, you don't have to count. It's a 50. So what's the point of this? Because I will generate y2 and y3. So I will have the label, y1 means the label, okay? The label of class 1 will be 1. So you just need to see my next two, you need to know what I'm doing. So I will have y2 means 2 times this, y3 becomes 3 times this. So all y2 gonna be 2, 52s. Y3 will be 33, 53s. So that's, in this case, I can easily mark my classes. Okay, and then what is the other parameter? -10, and then 8, 20, and 8. This must be 8 as well. And then 25, 50, and 0, -12, 20, 149. 50. Okay. In case you're not familiar with the multivariate normal distribution, I'd better. Okay, I'm lazy. Let me directly just multivariate normal. Let me just ask Wikipedia. Because otherwise, okay. So multivariate normal distribution is going to be the notation is as follows and mu sigma. Be careful, this mu is a vector, sigma is a matrix, in which the mu vector means the mean on each feature or on each parameter, and the sigma is, let's say, suppose I have p. Okay, let me directly write something. Suppose I have p features, white color. Let me use blue color. Suppose I have p features, so this mu will be equals to mu1 till dot mu p. It's a p-dimensioned vector, while the sigma matrix, let me write it here. The sigma matrix would be a matrix. A matrix is gonna be, let's say, sigma 1, 1, sigma 1, 2, until sigma 1 p, and the similar things here. Sigma p1, sigma p2. Sorry about it. It's just really difficult to write. P2 dot, and then sigma pp. And this matrix is gonna be symmetric. Oh, sorry. This matrix gonna be symmetric. In other words, sigma 1, 2 equal to sigma 2, 1. That's why just now, when I wrote this one, I know the other one must be where it is. This one, for example, I write this 6, I know this one must be 6. It must be symmetric. It must be positive semi-definite. Regarding what is positive semi-definite, anyway, I'm not introduce it too much. If you're interested, you can check my I forgot which references. I believe in the reference I wrote the multivariate normal distribution very clearly. I even added to Wikipedia for this part. Okay, and then let's have a look here. I generated all those data to be the training data. Now I can just simply plot the training data, which is plt.plot and then x1. So I first plot x1, which is group number one, sorry, which is group number one. Label equals to training data class one, and I can just copy and paste. Class three, RGB, x1 here, x2, x3, x2, x3, x3, DLT.legend. Oh, wait. X2, no, oh, sorry. 1 minute, I just realized one thing. Okay, so think about this. Here, my x1, uh, okay, here we go. So this looks like this way. Be careful because I randomly generate those things from multivariate. Actually, here's two-dimensional normal distribution. So the data could be different, completely different. Where the result? The data could be completely different from the thing that I showed in the lecture notes. So now I already have the training data, but I need to do the KNN classification, right? So how can I do the KNN classification? So what we can do is, first of all, we need to concatenate these three classes of the data. Be careful, here are generated by the classes. So actually I have already 50, 50, 50, which is 150 training data. But I cannot only train like this way. I need to concatenate all this training data axis all together. So I can write like this way, x equal to np dot concat concatenate. Here it's gonna be x1, x2, x3, and then x is equal to 0. That means I'm gonna connect this x1, x2, x3 by rows. So the structure will be like this way. Structure will be x1, x2, x3. So and then the big matrix will be here. You know what I mean? It will concatenate by rows like this way. So that is the thing. And then, okay, let me just click. Okay, now I can simply print x dot shape. So x should be 150 rows and 2 columns. So 150 and 2. So now I have my x data for y, the same thing, right? And p dot concatenate, because y is what? Y is my label vector, y1, y2, y3, x is equal to 0. And now I have this, I can train my model. KN classification model equal to k neighbor. And then here I do have a parameter called n neighbors. So I will have n neighbors equal to what? I forgot. What did I use? Equal to 5. Okay, so I'm gonna set equal to 5. This means set k equal to 5. Okay, now I can have what model dot fit x and y. X are and y's are the things that I just concatenated. And then I'm gonna have the test data to test what's gonna happen. But test data, I also randomly generated. I can just write like that way in case I make a mistake of this parenthesis. But again, here I need to see the number 15, 15, 15 negative, 15, 10, 10, negative 20. So I generate, oh, sorry, 1 minute, 1 minute. No. My fault. My fault. Okay, here, sorry about it. Here, the test data here in my slides, I didn't randomly generate it. Instead, I give them. The reason I want to keep consistent here is because if I remember correctly, in example 7.3, we will use this example. So let me keep it consistent. Sorry about it. Here, I give them the three training data instead of generating them. MP.array, and here, okay, so I have this 15, 15, negative 15, 10. Then the last one is 0, negative 20. Let me make sure my parentheses are correct. Okay, and then this is my test data. And then after it, I will predict the test data. Y predict equals to model dot predict x test. So here is a prediction. And actually, we can just print it to see which class it belongs to. So 1, 2, 3. That's why I made these three data, instead of I randomly generated. Okay, so the first data belongs to group one, is label 1. The second one is class 2. The third one is class 3. I know this is not that clear. Let's plot it. Plot this test data into our plot so that we can see it more clearly. So it will be, of course, here I'm cheating because I already know it, but assuming I don't know it, okay? So I'm gonna say for, let's say, I in range of x test dot shape 0. That means how many x tests I have. And then I'm gonna say fy predict I equals to 1. That means it's class 1. So color marker, color make, wait. I always forgot the color marker, color maker, color marker. Why feel it should be color marker instead of color maker? Yeah, sorry about it. Here's the typo. It should be color marker, but actually it doesn't matter. It's just a name. I can make it a color marker equals to red X and the label equals to test data plus 1. And then I'm just lazy. Let me copy and paste. Make sure the indent are correct. Here I will have else if, and here will be else, because totally we only have 3 classes. Sorry. Here else. If equals to 2, then it's gonna RG, then GX, label number 2, label number 3, BX. You may ask, so why you write like this way? To be honest, just because I'm lazy. So use the way that we wrote before. We can write like this way. What I mean. So so that's the thing. And I just want to make everything one line. Sorry about it. Here should be. I just want to make everything to be in one line to save the space. There's no difference if you write it to be multiple lines. And now I can plot plt plot, let's say x test I0, x test I1, and then color marker. Is it color marker? Yes, it's color marker. And then label equal to label. Okay, here we go. Then you can see this is number data 1, data 2, data 3, and indeed they are corresponding to this is class 1, class 2, and class 3. That's the reason why I need to fix this instead of random, because random it can jump anywhere. Of course, you can run different times, the result will be different again because the test data are randomly selected. So here's the things. That is how can we make it. I believe I have the marker size here. Yeah, marker size is 10 because here the marker is so small. Marker size equal to 10. Oops. Whoa. Okay, now they're bigger. Okay, so this is the very basic running of the KNN. Okay, then let's go to example number 3. So here, of course, for each data, I can run a test data everywhere. Test data looks good. But sometimes we would like to have something called decision boundary. So decision boundary is a more intuitive like view. So you're gonna immediately see which one should be, class one, which one class two, which one class three. So for example, here the decision boundary like this way. And let me see. I don't know how did I make this data. I don't know how did I make because I'm curious in this area why this in this shape it is. Oh, that means I guess here k equal to 3 maybe. Yeah, you can see here, for example, if I choose 3, indeed, these two green points are actually closer. And that's why all this area is what is actually green area instead of red. So basically here's how can we plot the decision boundary. The trick is here, you're gonna first of all use np.meshGrid to have those components span the whole plane. And the second thing is we're gonna use something called plt.pcolorMesh. So pcolorMesh gonna plot all those coverage based on the mesh grids that you generate, and then do the class make this kind of classification points like this way. So by the combination of these two, we can actually make the decision plot, the decision boundary. Okay, let's say here. So here, let me show it here. Generally, all other things are same, but the basic difference, the key changes are here. But here we have several new things, which is dot ravel and also dot t, and then let me just code it. I believe by coding it's easier for explanation. Let me insert a lot of things just in case. Okay, and to make my life easy, let me still copy and paste, and we will still choose. I believe. Let me see. Did I still choose this point? No, I don't need the points anymore. But I should have. Come on, sorry. I need to change the parameters because here, I want to make the parameters all the same. X1 equal to 5, 5, 36, 10, and then 10, 36. Okay. 50, and the second one is negative 5, 5, 49, 12, 1255. Last one is 0, negative 6, 36, 1, 149, 50. Okay, here we go. And then let me make sure I have the color. Give me 1 second. Yeah, here I need to include this one. From math plot led dot cost plot led dot color import listed map. What do you call it? Listed color map. Just don't show me the hint. Okay, and then I know I will ask for the colors again. So let me just make it here. Oops. I don't need to print this anymore. I even don't need to test data anymore. But I do need the word boundary color. And I will forget it, so I write it here first. Light coral, light green, sky blue. Okay, now I don't need it anymore. Okay, so basically what we're gonna do is first of all, we generate this data, then we can plot the area here, then we have X concatenate, then we fit the models. Okay, till here, everything the same, but the difference here, okay, now I already have my boundary color. What I'm gonna do is first of all, remember what we mentioned here, which is the basic idea to first use mesh grid to generate the mesh grid of points on a plane, and then use plt.pcolorMesh. Okay, now I'm gonna have x equal to np dot linear space. Linear space. So I have generated all these axes, sorry. And then the zeroth one to be the main. Here, okay, we can see the STD, the sigma is about 10, so 12, 1. So I believe I might not my 10. Yeah, I minus a plus 10. But this is really not a really big deal. So this just shows you that how far it will be. Let me show how far it will be, from sorry, how far it will be from our last point. So, I mean, people may ask, so why write a -10? Why don't you write -5? I mean, really doesn't matter. It's just, it's something like the space that what you want to leave dot mean, sorry, dot max plus the 5. And then y gonna be the same, but it's gonna change from 0 to 1. Okay, now x y equal to np dot mesh grade. Okay, now already create everything in my plane. Next, what we need to do is to make a prediction of the whole decision region, right? Okay. Yes. But here I need to mention several things before continuing. The first thing here is something called ravel. So first of all, let me just to make my life easy, I'm gonna just disable all the plots temporarily, to make it faster. Let me see. Okay. So first of all, let's print the dimension of x. Print x first. You'll see. How matplotlib dot color. There's no color. Oh, colors. Sorry, colors. Okay, here we go. Did I put an R here? Oh my God, that's great. Okay. Cannot import name. Why? Oh, give me matplotlib dot colors import listed color. Sorry, listed color. So here would be wrong as well. Not list color, listed color. Listed color map. Okay. So here is not the artist. I don't matter. Here is my XX. Looks very messy. Let me put XX dot shape. Now, wait. What happened here? Why there's a plot here? Give me 1 second. Did I plot anything? Oh, because I have this. Okay, I just make my life clean. Okay, so you can see the shape of XX is 50-50, meaning that it has 50 rows and 50 columns. Okay, now let me print it like this. First print XX dot shape, right? I'm gonna print XX dot ravel, and you're gonna see what's gonna happen. So this is XX, which is 50 by 50. This is X ravel, and I can print ravel dot shape as well. And you will see it becomes a matrix. Sorry, becomes from a matrix to a vector. And this vector, the dimension is 2500. And you see what does it mean? So first of all, observe the first column, the first row of XX. You're gonna see the same numbers, right? And then after the second row, the third row until the last row. And then basically what dot ravel does is I will flatten a matrix or even a tensor to be what? To be a row, to be a vector. So basically here I have 50 rows, 50 columns. Then I will flatten this matrix by rows. In other words, it will be this direction. It will be it will go the first row first to be the first 50 numbers, then the second row to be the next 50 numbers, the third row to be the next 50 numbers, and we know 50 by 50 is 2500 until the last row. So this will give me all the 2500 elements in one vector. So this is the meaning of the ravel. This is a row vector, by the way. Okay, now let's go back. Why do I need to mention this? Because here we're gonna have a decision region predict equal to, you say, okay, easy, just model dot predict. Let's say you may say, for example, I put XS YY inside, isn't it down? No, it's not. Be very, very careful. Here it is 2D, and remember we just mentioned dot ravel. So basically what you want to do is something like that. You will make XX to be one vector, row YY to be another vector. So in other words, it will be something like this way. You want to make it, give me a second. How can I make the zoom? Okay. So basically you want something like this way. You want something kind of like the prediction. You want to have x as one call. Let me recall it. You want to have x as one column. Be careful. This is a column, okay? And the y to be another column. That's how you can remember it before how we do. We say, let's say the previous example, we say what? We say model dot fit x, y. And then predict is x text. But what is the shape of x text? Remember it? X text, the shape is just three different rows, meaning three data, right? So similar thing, you will have xx1 versus yy1, xx2 versus yy2, xx3 versus yy3, until remember how many we have 2500. So we have xx 2500, yy 2500. You need to make it to this shape. So how can I make it this shape? First of all, what we're gonna do is to use the Ravel to make a kind of a array, np.array. You be very careful here because here it is super easy to make a mistake here. Empty array, let me see. I will have x dot Ravel, y dot Ravel. And be careful, Ravel will give you row vectors. In other words, what you have now is actually this xx, y, xxt, yt. It will be like this way. But this is not what we want. We want the transpose of it. And hence, what you need is this dot t. That's what you need. Okay, let me before running it, let me show you something here. So let me first of all show you xx.ravel.shape and the same thing for yy.ravel.shape. It should still be the same thing, right? Okay, now let me do this. This one dot shape. You see it? It becomes two rows and 2500 columns, but this is not what we want. What we want is this. I put a T, which is transpose, become 2500 and the two columns. And this is indeed what I should put into the model dot projection, because exactly the same thing as what we did, y predict equal to model predict x text the same. The number of observations or the number of training data should be what? Should be in terms of the rows. So here I should have 2500 training data here. So now let me put it in this way. And then let me run it just in case something's wrong. Okay, you can see it's correct. And by comparison, if I remove this dot t, you'll immediately see wrong number of features. Let me see, where is the error information? Okay, X has 2500 features, see it? But the k-nearest neighbor expecting two features as input. That's the trouble. You know what I mean? That's why this 2500 is not the features, but the train number of observations or the number of training data. That's why you do need such a T dot transpose. Okay, now we have already had so many transpose. So many kind of like the test data or decision region. For each data, we make a prediction. Now we can use what? We can use the P color mesh to plot it. Okay, so now let me remove all those printing things. Oh, sorry. Where's my okay? Remove all these printing things. Now I can use plt.p color mesh. So oops, sorry. My first will be x, y, and then be careful here. It will be because your D predict. Let me just let me print it again. Print dd predict dot shape. dr not dot dd. dr predict decision region predict dot shape. You will see it is a shape of 2500. But what is the shape of x and y? They are different, right? They are 50 by 50. So you can reshape it manually, put it 50 by 50, or you can write something like this, which is a way to be lazy. Predict dot reshape. So this means, okay, reshape your dr predict decision region predict to be the same shape of xx. So now we can just make a C map equal to boundary color. Boundary color. So here we go. And in this case, we can just color, make it a decision region and make the colors here. And now let me just plot it. Okay. Great. Wrong spell. Again, this will p color match. Here we go. Oh, why there's as a p color. Oh, what so wait. Oh, because of here, I forgot. I commented, I need to uncomment here. Okay. Okay, here we go. So that's the thing. And one more thing is here. How many did I generate? How many did I generate in my 200? Okay. The more you generate, the less saw you will see. Otherwise, it will be, you can see here we didn't generate many points. You can see a lot of saws here. But if I make a 200, it will be much more smooth. Okay, here we go. See, it's much more smooth. Of course, you can make a 2000, but it's gonna take a lot of time to calculate. And in this case, we did have printed the decision region. So here is for k equals to 5, if I remember correctly. Where's my where's my you know why it can still run? Because we have already run the previous example. So it remains the model equal to the previous example, not this example. And to rerun it again, sorry. Otherwise, I show you error. Okay, here we go. This is more, this is closer to our examples. So because that's also the reason why I do need to check the parameters, because the parameter change will be very different to generate a random multivariate normal distribution sample data. And here we can see. Let me make it to be. Let me make it out. Okay. That plot lab qt. So this will make the plot out instead of inline. Okay. So this is the thing. I know it's ugly, but at least we do have a decision boundary. Again, what we do is we get the mesh grade, and hence we get a lot of. Let me use a color. Let me here put points here, and then let me use a yellow color. So we generate a lot of those kind of points here. Like each line 200, each column also 200. Total, how many did I generate? Let me see. Yeah, I believe I generated 200 columns here, because before I didn't put 200 here. Now, for example, if you print axis y, it will be different. Let me print this. Print, let's say x dot shape, and then dr predict dot shape. It should show you oh wait, the capital DR, sorry about it. It will show you like 240,000. Where it is. Run it again. Okay. Okay, 240,000, see it? And that's why before only 50 by default. That's why it has a lot of source not smooth. Now it's more smooth. And indeed, we generate all those components, 200 in each line, 200 in each column, and totally 40,000. And then we make the prediction for each of them. And then we use this one to color it. And hence, you can see the decision region. And that's how we use the mesh, the MP, the mesh grid together, combine it with the p color mesh, and then we can make a decision bound. Okay, so this is the thing. And of course, this is only for one hyperparameter k. What if we change the hyperparameter k? Because here k equals to where's the code? Here the code k equals to 5. Here k equal to 5. But what if, let's say I say I want k equal to other numbers? Similar thing. You need to use a subplot. Okay, here's the case. Let me see what are the numbers. I believe the same parameter. Yes, 1, 5, 10, 20. Okay, 1, 5, 10, 20. Let's copy and paste everything. But I don't want to print it anymore. Okay, 1, 5, 10, 20. And then let's see which part do we need to change. So first of all, x and y here. Let me see. Here I need to make it down here. And then x equal to this, y equal to this, and then this one won't be changed at all, so that I can have this one here. And also I need this one because I don't need to use it again. So I can have x, y, y. So this tells you how I gonna generate what the points on the plan, the mesh grid, and then have this one, and then paraboid, and then key classification. Let me see. Okay, now I believe I can make it here. First of all, I will generate a figure equal to plt dot figure. And then what I'm gonna have is I need to have a subplot, but let me see, k list equal to 1, 5, 10, 20. Am I correct? Let me see. 1, 5, 10, 20, yes. And then I need an I to make it a subplot. So now I can make a 4k in k list. So what I'm going to do here is first of all I need to run the k classification. So here equal to k. I don't just set k equal to 5 anymore. Okay, and now I'm gonna fit x and y still correct, and then I need to do this one, which is dir predict, because I've already had x and y, so that I already have this one, and so that I have this. And then after it, I just need to plot, right? Yes, I need to plot the training data. Plot the training data, and then let me see, I need to add a subplot here. So I need to have x equal to figure dot add subplot uh subplot or subplot. Let me see. The thing is, it doesn't. Let's say, let me see whether it will show you an error. Okay, here we go. Okay, that means it's subplot. Subplot if you want, and then here you'll make everything to be x, and then x, x. Okay. Now you will have let's see subplot here, the decision region. So here's the thing here, and then I'm gonna have set title. Let's say kn for k equals to k, and then ax dot legend, and then I plus equal to wait, I cannot. I plus equal to 1. So finally you will have this one, you don't need it anymore. Okay, that should work. It's nothing wrong. Where it is? It's here. Oops. Well, there are so many. Oh, I run it too many times. Sorry about it. Let me close all of them. It takes some time. Yeah, sorry. Let me rerun because I run too many times just now. Okay, here we go. I should have k equal to 1, 10, 5, how many? 1, 5, 10, 20, 4 subplots. And okay, here we go. So that's the for k equal to 1, equal to 5, equal to 10, equals to 20. And indeed, you see, for a small k, I have more those kind of island. And for a bigger k, those kind of islands are smaller and smaller, because it's kind of like a more harmonious, the prediction is like, because somewhat like for a bigger k, it's gonna be more consistent, let's say. However, be careful that bigger K doesn't necessarily mean a good point, because bigger K is easy to make it to be overfitting. Be very, very careful about it. And what you may get confused, you may be surprised that in many applications, we set up K equal to 1. Simply because it's the fastest way, and also k equal to 1 somewhat can give you very, very good results. So that's how we do the KNN for subplots. Okay, now I can close this one. Okay, now yeah, the same thing. You can see many those kind of islands here, and there's some statistical results of this. If you're interested, you can read it here. Let me see where this lecture 7, 10 years neighbor. I believe I proved some analytical. It's just so slow. Okay. Oh, I didn't even download it here. How can I download it? Download. Okay. But basically, I believe I showed some I show some here we go, some statistical results of this. And also I believe here's some analytical kind of convergence and something. Indeed the truth is that, well, the KNN is actually very, very powerful because it's super, super fast. And the results, in many, many cases is even better than those kind of more complex method classification methods. Okay, and then the next one we want to mention a little bit a very fundamental example, or you can consider it as a very small project, as how can we use the KNN in image recognition or some images. So here, KNN name as K nearest neighbor. So when we say nearest, that means we need to define distance or a metric. Otherwise, what do you mean by nearest, right? So in all previous examples, the nearest we define by the physical distance or the physical Euclidean distance, which is true norm data. But in many images, you may consider the color instead of only the distance, or you can code it to be color including the distance and give it a weight. For example, let's say color 50% and the distance 50%, something like that, you can do it. And in this specific example, we just consider the color because the example here is I'll give you a map like this. This is actually the map of a university. It's right here. Allow. I give you the map of the university. Let me see how can I layers. Can I uh let me see satellite labels. I can okay, so now it's gonna be more clear. So this is the university. So we have the buildings here, we have the parking lots here, we have a street, we have the grass, those kind of things. And I wanna just ask you, so this is a picture. Given some training data, I'm just randomly choose a point. For example, I can choose this point and I want to ask you where it is. So you should tell me it's a building. Where it is, you should tell me here's a parking ground. Where it is, you should tell me here is like grass or tree, those kind of green things, right? So that's my point. And in terrain research or geographic, this is very important because, for example, I can directly tell you, hey, consider, for example, suppose I consider a box, let's say, consider this region, for example. Can I make it bolder? Let me see. I don't know how Zoom gives me line width. Okay, here's bigger. Great. So consider this region. I'm gonna ask you, hey, among this area, what's the percentage of the grass or the trees? What is the percentage of your parking lot? What is the percentage of your street or buildings, right? So with this, everything I can calculate. And more powerful thing, you know what, is a tumor research. Tumor research machine learning. Let's say classification or tumor detection, let me whatever things. I don't think I include an example here. Let's say tumor detection, machine learning. Okay, so more powerful things, something like that way. Say I give you a picture, of a patient's, MRI scan, and I want to ask you, hey, is this normal? If not normal, if not normal, which part is not normal? So for example, look at this one. I don't know whether it can be. Can I just see it? Can I just? Oh, okay. Here we go. So like for example, this where the part something. Okay. Here's something we want to search. Find something abnormal. Let me. Sorry about it. Let me have a look at this example. So this is a probably a tumor, and I want to ask you, hey, how big the tumor is? Big in terms of, let's say, totally your head. The size of how much and how much the tumor is. So first of all, you need to detect the tumor, and then you can use something, for example, like the pole color mesh to color it, and then you can calculate how many pixels or what is the size of this one versus what is the size of a whole head, and then you can detect. And also you can make something like XY location, you know what I mean? And then you can detect, give a like how dangerous a dangerous score or something level of the tumor, something like that. I want everything to be done by machine learning instead of by human eyes. Like similar here, you can see this part is abnormal. But first of all, how do you know this is abnormal? Second, if you know this is abnormal, how large it is. So basically, all these are just classification, things. Okay, let me continue here. Uh, uh, first of all, we need to if we want to use KNN, we need to know what kind of distance or what kind of metric we use to define the distance. In this small project, small example, I use RGB color. RGB means red, green, blue. It is a very fundamental way to code the color. I would say almost all our human, human eyes recognized recognizable colors can be coded by RGB. So it's gonna be something like that. It will be something, for example, let's say 200, let's say 100. So this is the RGB color, means red equal to 1, green equal to 200, and blue equal to 100. So, and each number should be from 0 up to 255. So that's the definition of the RGB. So this gonna give you a color level. Of course, if you are serious in those kind of like image, processing projects, then you will have different layers. One layer is RGB, another layer is luminance, and the third layer, sometimes we call it like the filter layer, transparent layer, which is somewhat what we're gonna do for filters on image features. And then if you want to have segmentation, then you may really consider that kind of layers. And I don't know whether if you've watched those kind of videos nowadays, like colorize a video, which is by machine learning. But here's by machine learning, okay? It's not by some traditional methods to colorize it. And how can we make it? How can we recover, a video from, let's say, black and white to be RGB color? So all these kind of things can actually, be done by those kind of classification things. But anyway, sorry about it, a bit too far. Let's go back to this example. Okay, so here we're gonna have RGB to be the distance, and again here we use the Euclidean norm, which is, suppose I give 2 pixels with 2 RGBs, and then I'm gonna calculate the distance of these 2 pixels to be like this way. So this is the thing. And thing number 2 is something called the pixel recoding. So for a picture, of course, it's composed of many different pixels. We can definitely, consider each pixel to be a unit or a pixel. But sometimes it could be very biased, because especially if your pixel, if your image is large, sometimes, it's not that harmonious. So if we can recode the image, we can kind of like a data pre-processing. We can make the image like better for the future, like classification or do whatever the things. So one of the most popular method is to get the average, RGB. So for example, consider this pixel number 5 in the center. Instead of directly using itself, let's say the RGB of this pixel itself, what I'm going to do is that I will consider all the average of all the pixels surrounding, including itself. So here we should have, including itself, we should have 9 pixels totally. And then we should have 3 times 9, which is 27 values, which means 9 R's, 9 G's, and 9 B's. Then what I can do, one method, for example, is to get the mean of all these 9 pixels, and then make that value, the R mean, G mean, B mean, be the RGB, or be the data of this target data's pixel. So this is one method. Another method is we can directly, instead of getting the mean of RGB, which is 3-dimensional data, we can directly consider it to be 27-dimensional data. And then, so for each pixel, it will be somewhat to be 27. But the second method has some problems. Problem number 1 is that it is, requires more column space, because here you expand the space from 3D to 27D. Another problem is that what if, let's say, I have a pixel at a corner. So at a corner, I only have 1, 2, 3, including myself, 4 neighbors. How can you pixel 27? You may say, okay, I add dummy data to the 23rd to the other 23rd elements. But what kind of dummy data are you gonna put? It will really cause a problem. So the first method is actually way more practical, and we use those kind of recoded unit or recoded data as a training data instead of the original the raw data itself. And then let's see how to do it using this example. So as I just mentioned here, I will simply classify the terrain into 4 classes: buildings, parking lot, trees, and glasses, or you can say greens, whatever it's called, 4th Street. And let me see here. So by our eyes, we can see that, for example, this is a building. All these kind of dark colored are or gray colored building. Something a little yellow is those kind of parking lots. Or actually, parking lots and streets is very difficult. I believe in homework there's a problem which is you need to consider both color and the physical distance, so that it will kind of help you to differentiate parking lot and a street, because otherwise you see all the colors the colors are so similar. It's kind of like very difficult. And then the greens are actually the easiest one to directly use RGB. I believe the new Google I believe the new Google data is better. Yes, the new Google data is actually more friendly. The data I used was 4 years ago. So this is which year? 2024. Oh, great. The newest data. Okay. Now let's see how can we do it. By the way, the data is uploaded here so that you can play it at home as well. And you are very free to use your home data or the play here. Here's the data. Let me see. Here's the figure and here's the data. You can also do it from Google Map, of the community that you're living. You can play the same game. Okay, so and then you will see like how many grains you have, and then you can check your government data to see whether the constructor fit the requirement. You don't have to manually measure it. You can use the machine learning algorithm to measure it. Okay, anyway, so let's see how they do it. Let me see here. So the first thing again is I need to load the data, and I will have a look at the data. Let me have a look first. Okay, I need to read the original data. And, oh, okay, right. Okay. So first of all, here's because it's very important. So let me write another markdown. Example 75. Okay. And then to make my life easier, I believe in my slides, I wrote everything in one because I have a line number. I believe in my slides, I wrote everything in one cell, but here I'm going to separate two different cells. So first of all, let me import. Okay, let me just copy and paste. I'm just very lazy. Okay, I can copy and paste everything. And I do need one thing called a CSV. And for the CSV, I can handle those kind of folder reading things for file. I said folder. I shouldn't say file. Reading, writing. Okay, so and then let me also put a matplotlib qt, make it outside. Okay, the first thing I need to do to read the original image. By the way, I put those dash lines as to let you know it's kind of like big part, because I will have some sub like comments in the middle. So plt dot figure, and then image equals to plt dot image im read or image read. Okay, and then it's gonna be, let me see here where it is here. Then what's the name of this one? Let me see. JPG, okay. .jpg. Okay, now I'm gonna already read this one, and then I will give it a title, and because I will basically just show it. Plt.title original image. Plt.imshow image. Here we go. So in this here, I already showed this image. By the way, be careful that I specifically leave this axis here on purpose, because I remember in the fourth part you will see this image show is the y-axis is opposite to the PLT plot, because remember for PLT plot, our y direction is like this way. So from here to here, it will increase the y, in which, this is the point of y equal to 0, equal to 1, equal to 2, increasing. However, didn't you see the axis here? The y is actually go from this direction. Be very careful. Later in the last one, you will see what I mean here. It go this direction, you see? And to be honest, I don't know why they set up like this way. The y equal to 0 is here. And this actually will make a chaos in many applications. But anyway, so this is how I can see the image. But this is just our human's eyes. How does everything, stored in let's say the picture in the computer, or how can we read its real RGB here? So for example, let me Let me show it here. So for example, you can see my cursor is right here, right? And you can see, did you see this part? Pay attention to this part, okay? You can see here shows you x equal to this, y equal to this, and do you see the three numbers? The second line. For example, here you can see it's 86, 91, 87. This is the RGB color. And then here you can see this part is 48, 45, 84, 40. Okay, so these are the data. And then how can I really read it, see everything? So here I'm gonna say, let's say write the image data to .csv for observation, let's say for observation. Okay, now what we can do is this. That's why we need to have the CSV. We have call this with open, and let me copy and paste here. Actually, I don't matter down here. Let's say image. So this means I will write. I will open. Let me finish everything first. Inline equal to call empty add file. And then 1 minute. I have to define the file writer first. Writer equal to CSV dot write. Yes. What you're gonna write is this file. And then file is all this thing because we have this as a file. So this is the file. Delimiter. Anyway, let me first write it down, then explain it. You could do empty. No, I'd better have a comma here. And then I will have file writer dot write rows. I will write it in rows instead of in columns and the image. And then, okay, now if I run it, what's gonna happen is that, so sorry about it because I was just, running this one before, okay. So this line will give you a new CSV data called image.csv. This W means I'm gonna write it inline empty. That means just, let me see. No, you don't need anything. So in some cases, inline, I can use this inline to add something, let's say /n, something like this, to force it to change the line. And then this dilemma means two different data in the data. How can I write it? Like I writing this way, what you're gonna see is between data, it will be a comma there. But let's run it. Let me just run it. Oh, great. What is the inline is? Let me see. Sorry. It's not inline. What's the name? New line. So. New line. Matplotlib lab is inline. Okay. Now I run it. What you're gonna see is see it, and you can see we just created. You can see the time. Okay. So we just created this one, and I open it. You will, yeah, here we go. You will see what does it looks like. So each cell is the RGB. For example, this cell means RGB is 179, 180, 164. This one is similar. And then if you open it, sorry, let me close this one. If you open it by text, notepad, what I mean is, okay, you see the comma here. That's the reason I add where it is. That's the meaning of delimiter here. So that means between two different data, use a comma to between them. So that's the meaning. And then W means write. And so basically you will write the image to this one. And the very interesting thing is here. Well, I have so many. Let me just close two. Let's say I just open the third one. So what it shows you is this. For example, let me see the very first this corner data. 176, 176, 177, 161. Okay. Now have a look at the data here. Remember the number 176, 177, 161. Okay, let me put it here. I just cannot. See, I need to really fix my mouse. I cannot move. 176, 177, 161. See it? And then the next number, 179, 180, 164. Okay, let's go back. 179, 180, 164. You see what I mean? What that means, the RGB, pay attention here. It will show you the RGB data. See it? And then the 179, 180, 168, 164. See it? So this is really row column corresponding data, and how that's how the computer read and make an image. It is by this data. Be careful, here's a tensor. Why? Because this is a 4D. So for example, here, this one is a 0, 0. The 0, 0th data is a row which is 176, 177, 161. In other words, if I want to express this one, it is what? It's image 0, 0, 0. This is 0, 0, 0, 0. Sorry. This is 0, 0. Oh, I'm a little confused. Sorry about 0, 0, 0. And this is 0, 0, 1. This is 0, 0, 2. Okay. So this cell is 0, 0. Okay. So it's a tensor, but I don't have to save it. That is how those images are stored, are saved, and be read by computer, and finally here show you an image. But again, I mean, this part is not really necessary needed. This is just, purely for observation, because I want to let you see how the image will look like. Okay, now the second step is one of the keys, which is to recode. Remember what we discussed here? What we want is to use the average of all the neighbors, including itself, okay, to be the pixel data here, instead of just use itself, which is a bit biased. Also, we should consider a case, what if it's in the corner, or let's say on the edge? Let's say it's here. So I only have 6 neighbors because, suppose this is my very 0th row. I don't have any, pixel data above me. So, you know what I mean? So we need to consider all these cases. And hence, we need to recode the image, let's say tensor data by using the mean of the let's say adjacent pixels, if it exists, of course, if it exists. Yeah. Okay. Let's see, how can we do it? So first of all, I create a matrix called image recoded equal to np.zeros. So originally, I make everything to be 0 because of what I'm gonna do. I will, plus equal to something summation divided by the total number of adjacent pixels. Here, let me make it image.shape. By the way, I'm interested to print the image.shape. Okay, so it is 320, 673. So this is the size of the image, and the 3 is simply just RGB. Okay, so I have the recorded ones, the tensor to be in this way, and then I have all 4i in range of image.shape 0. Be careful, image.shape 0 means the columns, not the rows. Okay, 0 is the columns. 1 is the number of rows. And then this is for the columns, and this is for the rows in range image.shape 1. Yeah. And then what I'm going to have is this. So first of all, I will create RGB equal to 0, 0, 0. And I will have another thing is called total adjacent, let's say pixels equal to 0. So find every time I will use R++ and a G++ and a B++ and a final number divided by the total number of pixels so that it will be the average. Okay. Now what I'm gonna do is for a given pixel here, I'm to decide, does everything exist? If they exist, then okay, I can do it. Or if they do not exist, then I cannot make it. Okay, so what I'm gonna have is this. For let's here, let me see. Give me 1 second. Give me 1 second here. Okay, for row in I-1, I+1, or column in J-1, J+1. So this is to ask, okay. So for each one, for each pixel, at most in the column direction, I have 1, 2, 3, which is suppose this is the ij. So I have I-1. Okay, I better write it here. The meaning is this. So suppose this ij So you can say this is what I minus 1 j, and this is I plus 1. Whoa, 1 minute, sorry, something is wrong. No. It is here. I minus 1 j. This is I plus 1 j, right? And for j, the same thing. This will be I j minus 1, and this will be I j plus 1. Similar thing. So the thing is, I'm gonna ask, hey, whether they exist. Sorry. Yeah, here we go. Whether they exist or not. If they exist, then I can do the plus plus. If they do not exist, then skip. Don't do anything. Okay, so that's how we have this. So how can we say whether they exist or not? Simple. You can use if. Again, this is not a format. I just I write it just because I'm pretty kind of like lazy. Less or equal to, so 0 is the minimal number. What's the maximum number? The maximum number must be image dot shape 0 minus 1. And also here, less or equal to colon, less or equal to image dot shape 1 minus 1. The reason I put a minus 1 is because the last index must be the number minus 1 instead of the number itself, because the first element is 0. Oh, as the first index is 0. Okay, so if this satisfies, that means what? That means, okay, for this row column, it does exist. If it does exist, then we can do R plus equal to image row column and then 0. That means I'm gonna make the R to be the R plus my current R and do the same for G and B. So R plus the current R, G equal to G plus the current G, B equal to B plus the current B. And now let me see where I should be here. So this IJ is the target column, row column pixel. Okay, and now I already have all the summation of all the neighbors of R's, G's, and B's. Sorry, wait, I forgot one thing, which is total. Total plus equal to 1. That means, okay, I have one more adjacent column. Be careful here, it includes itself as well, okay? So now, after everything, so this one should be around here. Okay, I can do the mean. So image recoded, ij. This means in the ith and the jth row of it equal to what? The average of everything. So here, be careful, RGBs, they are all integers, and hence you cannot use this one, you need to use double. So this double slash means divide and get an integer. R, this one by total number of adjacent matrix. B, similar, total adjacent matrix, and then RG, not B, sorry. And then B equal, okay, now I have recoded for the ij's, element for the recoded. And then I know you will be interested, hey, so what does it look like? Okay, so we can use the same thing here again. But you will make an image, let's say recoded. Coded. Let me clear all the plots as a file. Here, I don't need this anymore. As a file, and then file writer, this is image, not image anymore. It will be image recoded. Okay, now, so before I run it, just to let you see that here I just have one image. Okay, then I run it, it will have some image recoded. Where it is. Okay, here we go. We have an image recode, and again, you can see the time 6:49, 6:49. That means I just generated. Let me open it and see what it looks like. Huh? Anyway, not a big deal. Okay, and then again, sorry about it. And then what you can see here is this image is 177, 178, 162. Why? Then if you open this one, you will immediately know why. Okay. For sake of my life, I just calculate the first element. Okay, you can see. So basically, according to the logic for us to recode it. Basically, how shall we get the number of this? Let's say for the R number, it should be the average of 176, 179, 178, and 178, right? So what it should do is like this way. 176 plus 179, okay, the R number, okay, because the adjacent pixel of this corner is only this one, this one, this one, this one. Plus 178 plus 178, this one divided by 4, 177.70. So it should be 177, right? Yeah, 177. See it? And you can do the same thing for 178 to 168. Okay. So similarly, let me randomly pick up a pixel. Let's say this pixel. How do we calculate it? Sorry, this is recoded. Let me go to the original image. This is my original image. Let me just make it bigger. Let's say this pixel. How can we get it? So this pixel, let me use this color. This pixel should be the average of all these surrounding pixels, right? So let's say 170, the first R, it should be the average of all these 9 numbers. The second one should the average of all these 9 numbers. So why here 9? Because I have 9 neighbors, and here I only have 4 neighbors. I mean, including itself. So that's how you use the code to calculate and get everything here. The name is image recoded. That's how this one is generated. Okay, now we've already finished the second step, which is to recode the image tensor by using the mean of adjacent pixel. The third step is what we need to kind of load the training data. So before doing it, let me first show you what does the training data look like. Training data here. Okay, remember the key of the purpose of this one is what? As given an image, I consider 4 labels: building, parking lot, street and grasses, and the fourth label tree and glasses, the third label, the fourth label street, right? So in other words, I want to just point to you a label, kind of like a what? Let me go back to the where it is here. Let me show the original picture again, so it's gonna be better. The key is that I wanna point out a random coordinate. Okay, so suppose okay, so for example, you can see here the coordinate here is about it's xy here. That's like, let's say 525, 76, for example. Okay, here's right 525. I just cannot make it an integer, whatever. And then I'm gonna ask you, hey, what is that? You should tell me this is a is that parking lot? Yeah, this is a parking lot. You should tell me this is a parking lot. And then I'm gonna give you another XY coordinate. I'm gonna ask you, let me say here, what is that? You should tell me this is a building, right? So this is my purpose. Then what we have is exactly the same thing. Row this, column this, row this, column this, class. So here I sorted by class. All this data are class 1. This data class 2, this data class 3, this data class 4. These are your how many? About 255, maybe 256 training data totally. Then I want to ask you, how do you want to train the data? In other words, how would you load the training data? So here load, what happened here? Load the training data. How would you load the training data? So first of all, I need to get to the path of the training data. Path equal to R, it must be like here, the folder is here, but I don't know the name of the apps. What is the name of this one? Okay, here we go. The CSV again, and then .csv. And now what I'm gonna do is the data train equals to a pd.read CSV. Okay, now I've already read the data here. Then the thing is, be very, very careful. Those, give me 1 second. Those data are just rows and columns. It's not the RGB, okay? In other words, what we need to do is I need to read the rows and columns, and from these rows and columns, go to image recoded to find the corresponding row column data, and then read RGB. That's what I need to do. Okay, okay. Let me still keep it just in case. Okay, now I will have. Let me see. Let me see. Okay. First of all, I should have. Let me think about it. Okay, but at least my labels are correct, right? So I can already have the y train here. Y train dot equal to data train dot job. No job. Job is the other thing. X train row column should be job. Y train directly equal to let me see dot columns. The last one. Okay. The columns -1. So this is the last column of the what? The thing. Let me just wait. I I didn't. Oh, okay, okay. I have not loaded the PD. Sorry about it. Let me import pandas as PD. Okay, now it should be correct. Yeah, it should be correct. Okay, so from Python trained y train. Huh? Sorry, here's the thing. Not callable. Why it's not callable? True. Okay, here the y train. And indeed, they're the same. 1, 2, 3, 4, sorted by this. Okay. And then the next thing is for the X train. How can I get the X train? The problem is, be careful. Remember before we say is X train equal to dot data job, right? It's not X train. It should be X train row column. Why? Because these data are all row and columns. And by this row column, I'm gonna find the true RGB data from image coded matrix tensor. And hence what I'm gonna do is here data train dot job. And then which column should I job? I'm gonna job data data train data train dot columns -1. And then axis should be equal to 0. One column to drop a column. So now I have the X train and row column. So now I already have the row column data. In other words, for example, the first data is row equal to 111, column equal to 32. The second one, row equal to 15, column equal to 80. Okay, now I can use this one to get the data. So now I can have for give me 1 second. For I in range of let's say give me 1 second. Uh, Give me 1 second. Okay, it should be X train dot shape 0. That means how many data I have. Now I should have row equal to X train column row. This one is dot I log ith row and 0. So 0 means, this one. Let's say I equal to 1. So that this is I equal to 0, I equal to 1, I equal to 2. So this is the 0th element. That means the row number. The ith element is the column number. And then I can have column equal to X string dot I lot I1. And finally, I probably need to define X train because here I have not defined X train yet. X train I equal to, remember, I already have image recoded here. Now I can have it row column. You see what I mean? So in other words, oops, sorry, this will be an RGB, but this will probably be wrong because I have not defined an X train. I probably need to define X train first. Let me see. Yeah, X train not defined. So I simply just make it to be all 0. It doesn't matter. X train equal to MP dot zeros. Let me see. And then how large it's gonna be? It's gonna be like it needs 3 columns, and the rows should be X train row column dot shape shape 0, 1. Let me see. It's shape 0. That means how many observation data I have, and this is 3 means it should have 3 columns, R, G, and B. Okay, now I have X train here. Now I have this so that I finally should be able to run out X train. Yes, here we go. So in here I've already known what is the X train. And finally, I just need to train and code it. I just realized the time is not enough, maybe. Let me see how hard. Yeah, because it will still need some time for me to explain this image. Okay, let me temporarily stop it here. In the next lecture, I will completely finish it. And this is actually very interesting. Anyway, I will mention the remaining things in the next lecture. Thank you, and we will finish this one and try to have the haven't finished. The next one will be naive Bayes classifier. Okay, so that's all the class for today. Thank you very much, and have a good night. Bye bye.